This is a calorimetry problem where we're dealing with temperature change. We want to find the final temperature of a homogeneous, that means equal throughout, so it's a mixture, solution that's produced by mixing 40 mils of ethanol. So ethanol, you don't have to know the molecular formula for this problem, but it is C2H6O. And you're mixing it with a larger volume of water. Now, the ethanol is initially pretty hot. It's at 325 Kelvin, and water is at 298. You're given the densities of ethanol and water at these temperatures, or approximately. Ethanol is less dense than water. You're also given the specific heats of ethanol and water. So if you're making one homogeneous solution, then that means that the ethanol water mixture has a single final temperature. Or this mixture is going to be in thermal equilibrium. And heat is going to be released from ethanol because ethanol is at a higher temperature. So we can say that the heat released, or negative Q of ethanol, is equal to positive Q of water, because we're assuming insulation, or 100% of the heat is successfully transferred from ethanol to water without losing any to the surroundings. So if we're going to calculate Q, this comes, of course, in the form of joules, and we're given the temperatures initially. We're also given the specific heats and the volumes. So we can say that the mass of ethanol times the specific heat of ethanol times the temperature change equals the mass of water times its specific heat times its temperature change. Okay. So we need to find the mass. So for water, we know its volume is 60 mils. Water's easy. It's 1 gram per mil, approximately. And so it's 60 grams. Same conversion type can be done for ethanol. It's originally 40 mils of the mixture, and it has a lower density, 0.789 grams per mil. So if you multiply those, you'll get 31.56 grams of ethanol. Okay, so now we can plug these in. So heat is lost from ethanol. There's a negative sign there. The mass is 31.56 grams. The specific heat is lower than that of water, 2.46 joules per gram degree Kelvin. And then its temperature change is some unknown T final minus an initial 325 Kelvin. Once again, this difference here is the same in Kelvin or Celsius. You can really use either one. In this one, we'll just stick with Kelvin, so we don't have to convert, but you should be able to go back and forth between those. So that's equal to the mass of water, which is 60 grams, times the specific heat of water, 4.184, multiplied by T final minus its initial temperature. Water was at 298. Okay, so let's solve for T final. We simply need to collect some like terms. I'm just going to multiply through on both sides. So over here I get negative 77.6 times T final minus 325 Kelvin equals 251.04 times T final minus 298. Now we can get some expectation for where T final should be. The ethanol, which was at a higher temperature, should cool down. And the water, which was at 298, should warm up. So T final in these mixing problems, if you assume insulation, is always somewhere between the initial temperatures of the two substances, that were at different temperatures. So more algebra here. You need to distribute through, and you'll see that negative 77.6 times T final plus $25,220 is equal to 251.04 T final minus 74,798. So collect the like terms. I'm going to add the 74,000 to both sides. So I get 100,081. That's equal to 328.64 T final, and then you can divide. So for T final, I get exactly what we expected. 304 Kelvin, somewhere in that range. Now, this 304 is not in the middle of the range, okay? T final would only be exactly in the middle if you had equal masses and if they were the same substance, meaning the specific heats were the same. This 304 is favoring water. It's closer to the initial temperature of water, 298. Meaning that delta T for ethanol, the change in its temperature is greater in magnitude than delta T for water. Because it only takes 2.46 joules to decrease ethanol's temperature by 1 degree Kelvin for 1 gram of the substance. It's a lower specific heat, okay? Which means it takes less heat exchange to change the temperature. Or for ethanol, the temperature changes with less energy going in or out relative to water. The other fact was that water is more dense and it was present in a larger amount. So there's more water to go around, and therefore, on average, water's temperature is going to change less. So 304 Kelvin is your final temperature. Be really careful about the negative signs here, right? The one that's at a higher temperature should release heat. That should be negative. And the one at a lower temperature initially should be positive. It will absorb heat. Okay. So an unrelated question. This is separate. Ammonium chloride. Remember that ammonium chloride is NH4Cl. There's a cation, ammonium. Remember that EM refers to positive charge. IDE refers to negative charge. Chloride. So that's a solid. But this solid is readily very soluble in water. Or if you take this compound, it's a white solid on the bench top. And if you dissolve it in water, then you can't see it anymore. So placing it in water causes the cation and anion to dissociate from one another. Or it forms ammonium, which is now aqueous, meaning it's surrounded by water molecules. And chloride is a separate aqueous ion. So they break apart, as most or many ionic compounds do. But this requires some energy input. It requires 182 kilojoules per mole, or the reaction is endothermic. It won't occur unless you heat it up. And that's, of course, balanced already. Okay, so we want to think about how each of the following thermodynamic parameters will change, whether they will increase, decrease, or stay the same during this process. Now, we're told there's no change in the volume of the solution. So delta V is 0. Okay. So if there's no change in volume, then that's going to simplify the enthalpy and heat discussion. The system, remember, is the reactant before dissolving, that's solid, and the products. The surroundings is everything else. The most immediate surroundings are water, the other component of the solution, and then anything technically outside the solution. We normally just focus on the immediate surroundings, water. So heat is being absorbed by the system, or it's endothermic. So what that means is that the heat of the system is positive, and the enthalpy change for the system is positive. So I'm using lowercase d here, meaning delta. Remember that these are the same sign and equal in magnitude if you're at constant pressure. And I didn't mention constant pressure here, but in this case, there's no change in the pressure because there's not a gas being produced or consumed. We just have a solid that dissolves into 2 ions, or the pressure is 1 atmosphere. So this heat doesn't just come out of thin air. If it's absorbed by the system, then it needs to be taken from the surroundings. Remember that the enthalpy change, or excuse me, the heat that's gained or lost by the system is equal in magnitude but opposite in sign to the heat from the surroundings because they are in thermal equilibrium. That's the same statement we essentially used in the previous problem with the ethanol and water. Now, since the surroundings is giving some heat to the system, giving heat away, that means the surroundings is going to cool down, or it's going to decrease in temperature, right? And you know that because of the equation we've been using with calorimetry. It says that the heat associated with some temperature change is proportional to the mass times the specific heat times the temperature. And mass and specific heat are always positive. So if Q is negative, then temperature change must be negative. The reason you're told that the volume doesn't change is because work is dependent upon that. So let me mention here, since I haven't talked much about work yet today, that work is ordered energy that's used to do some productive process, and it's equal to the product of force times distance, where a force has the units of a mass, kilograms, times an acceleration, meter per second squared, and distance has units of meters. That gives a kilogram meter squared per second squared, and that's also known as a joule. So work is an energy unit. But for chemical reactions, where we're either producing some gas or consuming a gas, the work is equal to the negative external pressure that's applied times the change in volume. And we're told that this solution, because there's no gases involved, does not compress or expand. The change in volume is 0 here. So this is just sort of a definition for work that you should have in the back of your mind. No work is done. There's only heat exchanged. And finally, the first law of thermodynamics, recall, says that the overall internal energy change for a system is equal to the heat plus the work that's done on or by the system. Now, I'm not writing any subscripts here, just like I didn't there or there. And if there are no subscripts, then you assume it's the system. If it's surroundings, it'll be explicitly written. So delta E depends on both of these. But we said that the heat of the system is positive, Q, plus work is 0. So delta E should be positive. The system increases in internal energy. Okay. So you would expect that if you had a thermometer in this solution, the thermometer is in contact with water, the abundant molecule, then the surroundings, namely water, should drop in temperature because water has been transferring energy to the system, which is the reactant and product molecules. And this is exactly the reaction type that causes, for example, like a cold pack to work, because a cold pack is going to involve a chemical reaction that absorbs heat, and then it feels cold to the touch because the surroundings decrease in temperature. Whereas like hand warmers would work by being an exothermic process that would release heat, and then they would feel warm to the touch. The surroundings would heat up. All right, so then we'll do a math problem with that same reaction. How many grams of ammonium chloride should be mixed with 100 mils of water at 298 for the temperature of water to drop? So we're dealing with delta T again. We're assuming insulation. So ammonium chloride is going to absorb heat. We said it's endothermic. It's going to absorb the heat that's given to it by the water. And none of the heat is lost to the surroundings outside of the water. So all of it stays in the solution. So we simply need to relate these heat exchanges with a temperature change. But now we're given the final temperature. So we're not given anything in terms of information about ammonium chloride's specific heat. Okay, so we're not going to use that equation of N times C here. But we can relate this heat value back to the amount of heat required in the reaction. So what I want to know is how many grams of ammonium chloride does it take to drop by 5 degrees. And keep in mind, you're given other values earlier on this problem set. You have 1 gram per mil for water. We probably need the density since we have a volume. We also know that water in the liquid state is 4.184 joules per gram degree Celsius, which is the same as per gram degree Kelvin. Okay, these two values are things you should commit to memory for water. They may be given, but it's likely that they won't because we use them so commonly. So let's just figure out how much heat the water needs to give away if it's going to drop 5 degrees in temperature. So the heat of water would be the mass of water, which is 100 grams since it's 100 milliliters, multiplied by 4.184 joules per gram degree Kelvin. And we want it to drop. So the final temperature is lower than the initial temperature. So it looks like the water needs to give away 2.092 times 10 to the third joules. And that's the same thing as saying 2.092 kilojoules. Well, the ammonium chloride would require 182 kilojoules. It would take a ton of heat out of the water if you have 1 mole, a whole mole of ammonium chloride dissolving in water. So the actual amount of heat we need is a fraction of that. Okay. So let's do a couple conversions here. So I know that we have 2.092 kilojoules is the actual amount. And we're going to solve for a mass in grams. That value has to be positive. Negative mass wouldn't make sense. And we know that this heat is being released by the water and absorbed by the ammonium chloride. So it's negative because it's released by water, but I'm just going to get rid of that negative sign now because we can't have a negative mass in the end. So we know that for 1 mole of ammonium chloride, that's going to require 182 kilojoules. I put kilojoules on the bottom to cancel. Now we have moles, right? And then from there, we can convert from moles to grams. And 1 mole, we need to determine the molar mass of ammonium chloride. So it's 14 for nitrogen, 4 for the hydrogens, and 35.45 for chlorine. So I get 53.45 grams per mole. Once again, that's just a unit conversion. Kilojoules cancel, so do moles. So I get 0.614 grams of ammonium chloride. That's how much you have to dissolve in 100 mils of water if you want the water's temperature to drop by 5 degrees Celsius or 5 degrees Kelvin.